Good afternoon, everybody. It's 12 o'clock, so we'll go ahead and get started for today. The only reminder I wanted to give you for today is that next week is experiment number 1, and I think the material is going to align really nicely. We should get to talking about the material for experiment 1 today. When you go to lab 1, you do have to have your pre-lab done. They will be checking it at the door. The way the pre-lab business works is they'll look at it as you walk in. If you have it done, they'll initial it. If you don't have it done, they won't initial it. And if it's not initialed, you'll lose about 20% of the grade for your lab report. So I suggest that you do go ahead and get it done. And you might also find you don't have time to finish the lab. So check your lab Brightspace page if you're not sure of all the details, or drop into the Help Center. If you're struggling to get the stuff done, the Help Center is there for you to help you get that done before your lab period. Any questions before we start for today? No, looks like we're okay. So last day we talked about the height of a wave, transverse velocity, transverse acceleration. We focused on wave on a string in particular for a little bit. We made a new definition, the linear mass density of the string, mass divided by length. That's got units of kilograms per meter, typically. So we're going to pick up talking still about waves on strings, but we'll get to a slightly new topic or a new thing to think about. So this is a rope workout. I've never ever done this before, but it looks really hard. Can anybody confirm? Okay, getting a few head nods. So if we think about why this workout is really, really hard, it's because the wave carries energy, and the energy in that wave is coming from the person who's working out. So the person puts a lot of energy in, and it makes the waves travel down the rope. So what we're going to start with today is how do we talk about energy being transferred in a wave. So that's where we're going today. So what we'd like to do is find an expression asking how much energy is transmitted by a wave moving through a medium. So we're talking about mechanical waves that travels in something. If you've downloaded the notes already, you might notice that I've edited a sentence here, just to make it not specific to simple harmonic motion, just total mechanical energy of a moving object. So from a physics 1020 or 1050 approach, we can write down the total mechanical energy in something. It's a sum of the potential energy plus the kinetic energy. So that should be familiar to you. Just write that one down. So our total mechanical energy would often have a symbol of a capital E. It's equal to the kinetic energy K plus the potential energy U. And if we don't have any losses to friction and air resistance and things like that, then this total mechanical energy is constant. So if we don't have any work done by non-conservative forces, this is a constant value. So K is our kinetic energy. U is our potential energy. Because it's constant, it means that sometimes the energy is all kinetic, sometimes it's all potential, and sometimes it's a mix of both. Okay, so it transfers back and forth between kinetic and potential. So if we're at a point in a cycle or a point in a system where the total potential energy is equal to 0, so for example, if you're thinking about a car that rolls down to the bottom of the hill, at the bottom of the hill, the car would have 0 potential energy and maximum kinetic, so that might be an example to think about. So if U is equal to 0, then our kinetic energy is equal to a maximum value, and our total mechanical energy E is equal to our maximum kinetic plus our potential, which is just 0. And kinetic energy is given by 1/2 times mass times velocity squared. If we're maximum kinetic, then we're maximum velocity, so Vmax squared. People okay with that idea? So that's just a recap from some of the things you would have talked about in an energy chapter in your previous course. Now what we're going to do is we're going to take this idea We're going to apply it to a traveling sinusoidal wave, remembering that if we have a sinusoidal wave, each bit of the medium is moving up and down with simple harmonic motion. Okay, so every little bit of this string is moving up and down with simple harmonic motion because that's what the source is doing. So to get into the particulars of how we do that, the first thing we do is we look at our wave moving through a medium. Let's say our medium is a string. I'm going to look at one tiny bit of that string, a tiny bit we call an element. So this is our element. This is moving up and down in simple harmonic motion. And we're going to say that our little bit of string, it's got a length delta x, and it's got a mass delta m. So the length of it is delta x from here to here. And if we were going to put that little bit on a scale, it would have a mass that we would call delta m. Delta in general just indicates it's a small piece, so that's what the delta means. So this little bit's going up and down in simple harmonic motion because it's a sinusoidal wave, because it's propagated by a source moving with simple harmonic motion. If we wanted to write down the energy of this little element, of this little bit, we would say that it has energy equals 1/2 times the mass, which we said was delta m, times the velocity, v maximum squared. So far so good? So energy is 1/2 mv squared, v is max because the energy is all kinetic. So now we go to the simple harmonic motion business. If we have simple harmonic motion, v maximum is the amplitude of the wave times its angular frequency. V max is a omega in simple harmonic motion. So that's what we're going to do with our V max. If we wanted to deal with our mass, because taking that little bit of string and putting it on a scale is rather inconvenient, let's bring back the idea of our linear mass density. So mu is our linear mass density. It's mass divided by length. So it's delta x divided, delta m divided by delta x. That means our little bit of mass, delta m, is the linear mass density times the little bit of length, delta x. So let's put these two things in our energy expression. So we get 1/2 times mu times delta x times v max squared, which means we have a squared times omega squared. So this is an expression for the energy of this little bit of the string, this little bit of the wave. Questions to hear? So now total energy is a fine thing to think about, but it tends not to be as useful as power. So an important factor, an important thing to know about is how fast is the energy delivered. So you can have energy delivered from an ocean wave. If you get it delivered over 3 hours, it's very different than getting it delivered over 3 seconds, right? So let's find an expression for power because that tends to be a more useful thing to look at. So power has the symbol of P. You may or may not remember that it has units of watts, which is a capital W. Power is change in energy divided by change in time. Okay, so it's the change in energy with respect to time. Change in energy over change in time, that's the derivative. So we're going to take the derivative of what we wrote down for our energy. When we do derivatives, we can take our constants out front. So all the constants come out front. 1/2 is constant, mu is constant. The delta x is changing because we keep going along the medium. That has to stay inside. A squared is constant, omega squared is constant. We're left with d by dt of delta x. So the derivative of distance over time, that's the velocity of the wave. That's the wave speed. Okay, now let's put all that together in a form that we're going to be able to use. So the power of a traveling sinusoidal wave is 1/2 times the linear mass density of the medium times a squared times omega squared times the wave speed v. So there's the power of our traveling sinusoidal wave. Any questions? There's not loads we can do with this equation. It's a useful tool to be able to think about physically. Kind of the only interesting problem, and I would challenge whether or not it's very interesting, would be kind of a plug and chug example, so we'll do something like that next. So let's go back to our geologist and the box of rocks. So last class we did an example where we had a geologist, one's at the top, one's at the bottom with a giant box of rocks. The rope has a box of rocks attached at the bottom. The rope is 80 meters long. The colleague at the bottom gives the rope a little wiggle. He makes a wave on the string. Let's say that he keeps shaking it with a frequency of 2 hertz. So he's doing 2 oscillations every second, making pulses to go up to his friend at the top. We found in our last example the wave speed was 88.6 meters per second. Let's ask how much power is being delivered if we say that the amplitude of that wave is about 5 centimeters. Okay, so this is not a real deep question. We're going to take the things we know and put it into the equation we have. So we'll write down our equation for power. Power is 1/2 times mu times a squared times omega squared times v. Let's look at each of those values. Mu is our linear mass density. So that's the mass of the string, 2 kilograms, divided by the length of the string. This is our amplitude, 5 centimeters, 0.05 meters. When you do this equation, I would recommend you work in SI units. Watt is the SI unit of power. It's joules per second. So everything here should be meters, kilograms, and seconds. Otherwise, your units are going to get wonky. Omega is your angular frequency. That's 2 pi f. And v is your wave speed. That one's already found at 88.6. And from our last class, we found that wave speed by doing the square root of the tension divided by the mass per unit length. So that was what we did last time. So in our equation, we've got 1/2 times the mass of the rope, 2 kilograms, divided by the length of the rope, 80 meters, times the amplitude, squared, times the angular frequency, squared, so 2 times pi times 2 squared, times the wave speed, 88.6 meters per second. So the power of this wave is 0.437 watts. Okay, so this is a tool to let you figure out how much power is delivered by a wave. Maybe it would be more interesting to see how much energy had to be put into that rope workout. Maybe I'll do that next time we do the class. Okay, any questions here? The next one in the notes, if you've downloaded them, is another example, which is basically the same example, but it just asks you to solve for a different thing. So I'll leave that one for homework for you to work on, and you can check your answers as you get through it. So the next topic we're going to talk about, we spent some time talking about sinusoidal waves, analyzing those. The next bit we'd like to talk about for a little bit, and we'll stay here until almost the end of the chapter, And that's what happens when two or more waves come together. So I'll switch back to the computer. So here's a video. I grabbed it from that PhET simulation just because it's nice to be able to hit pause and stuff. So I'll just hit pause here. So you see I've got two waves. I've got one wave coming in from the left, it's traveling to the right. I've got one wave coming in from the right, traveling to the left. Let's look at what happens over time. I'll hit pause here. So here's where the two waves hit each other. They come together. That must be people gearing up for the climate action strike. Yeah, I think people are starting to get ready. That happens right after this class. If people are interested, starts over at the clock tower. Okay, where was I? Oh yes, okay, so our two waves are coming together from either side. What happens right here is that the waves have smacked into each other. You see that they're starting to combine here. For a moment it gets really big. And then they pass on through just like they had never met. So the two waves come together, they combine or they interfere. They make a new wave for a little bit, the string looks different, and then they keep on going. This particular one that we're looking at, we'll see that the waves come together and they get bigger briefly. So it's interference because they come together. This one is called constructive interference because it gets bigger. Okay, so constructive interference happens where two waves come together and get bigger. This sort of interference, it's completely a wave phenomenon. Objects don't do this. You can't put two things in the same space at the same time, but you can certainly put two waves in the same place at the same time. One example to think about might be sound. So two people can speak at one time and you hear both things at the same time. So any two waves can exist in the same time in the same place. So that's what happens when our two waves are both upright and they come on top of each other. You could of course have one wave right side up and one wave upside down. That looks different. So here's our two waves coming. This one is traveling to the right, this one is traveling to the left. One is up, one is down. Let's see what happens when they meet. Okay, they're just about to meet. Okay, oh, I hit pause at a really good time. So when they're right on top of each other, it completely flattens out, the waves get smaller. This one is called destructive interference. So if it gets smaller, it's destructive. Then they pass on through just like they had never met. Okay, so any questions about this bit? We'll go back to our notes. And a bunch of the stuff I was saying, I've got typed up on some slides, and we'll see that all again in a minute. So now, interference in general, that's the idea that two or more waves can overlap. They can exist in the same space at the same time. A mathematical description we use is called the principle of superposition. And that states when we have our two waves in the same place at the same time, the new wave, often called the resultant wave, that's the sum of the two individual waves. Okay, so you add those two heights together and you get the new height. So if we have our first wave traveling to the right, this is wave 1, that wave will have a height, y1. It depends on position and time. If we have a second wave moving to the left, it's going to have a height, y2, of x and t. And then when they overlap, we get a new looking thing. That one is called the resultant, most often. Sometimes, not as often, you might call it the superposition, so resultant or superposition. And the height of this wave is the sum of these two heights. So yr also depends on position and time. That's y1 plus y2. Okay, everybody okay with that idea? If you were trying to find an expression for this wave, two ways to do it. If you did this sort of thing in high school, you might have actually added them graphically, like drew them on graph paper and did that addition. You can also add the equations using various trig identities. If you do extra practice in your book, you might come across examples like that. I don't plan to ask you a question like that on a test, so I'm not going to do an example in class, but if you're interested, you can certainly go through it. So that's our interference and superposition. Next, we'll put up the definitions of constructive and destructive. So questions here? Yep.
Can we do a phasor diagram and get the resultant?
Yeah, you could do a diagram like that. That should be fine. Okay, so now here's our definitions of constructive and destructive. This is what I was saying during the simulation running. So constructive interference, it occurs when we get two or more. So I'm just going to do examples of two waves. Of course, there can be more than two. Two or more waves combine to create a larger wave. So here's our two waves. They come together and they make a larger wave for a moment. Destructive interference is we get our two waves coming together, and then our new wave is smaller than at least one of those two waves. Okay, so it gets smaller when we have destructive interference. For destructive interference, we do have one special case, and we get perfect destructive interference when it completely cancels. So if it gets smaller at all, that's destructive. It's perfectly destructive when it cancels completely for a moment. Okay, questions? So let's take our interference and we'll look at a special case. I'm going to throw this up as a picture of what you're going to see in the lab on Monday, and then we'll do a demo in class. Yep.
Is there a perfectly constructive?
You see, that's an interesting question, and I've wondered about that too. And I don't know that you could have perfect constructive, because I'm not sure what that would mean. Like, would it be two identical waves going on top of each other? Because you could argue that that would be perfect. But what if you had one wave and one that was twice as big on top of each other? Would that be even more perfect? To me, that kind of boils down to sort of a philosophical question. Yeah. So I'm not sure. I'm not sure that kind of means something. It's a good question, though. Okay, so when you get into the lab on Monday or Thursday, you're going to see a little device like this. It's got a little aluminum tab. It's attached to a string. It's going to vibrate the string up and down. And it's going to make on the string what we call standing waves. So I'll leave you to investigate that in the labs. I brought a slinky for us to try and make some standing waves in class. Can I get a volunteer to hold one end of the slinky? Yes, please. Do you mind just coming to stand up here, please? So you hold one end, and I'm just going to shake the other end up and down. Maybe you just come towards me a little bit, just so we can try and get the maximum point of view in the class. So here's my slinky. It sags a bit because it's a slinky and it's pretty stretchy. I'm going to vibrate one end up and down. And if you look at this, right now it looks like a half of a wave. Kind of see that? So at my end and your end, the two ends aren't moving very much, but the one in the middle is moving up and down a lot. So the end at my hand, I'm the source of the wave. I'm making a wave, it's traveling down, bouncing back. So our two waves are the ones I'm making, the ones that are reflecting back. They're interfering, and I'm shaking it up and down at just the right frequency to make it do this. It sort of looks like a half wave pattern that's standing still, even though the slinky is going back and forth. Okay, so now I'm going to try and shake it at a different frequency. See that? So at 1, 2, 3, 4, I think I got 2 wavelengths there. So when I shake it just right, I can get standing wave patterns with different numbers of half wavelengths, different wavelengths on there. So let's see. So there's our demonstration done. So you're going to see this with waves on strings, but this is not a bad demo to do in a classroom. And you might notice I said a couple of times I had to get the frequency just right to make this happen. Another thing you can do to get this wave pattern is you can make the length just right. So where we're going to go to next is talk about what exactly do we mean by the just right frequency and the just right length. to make this standing wave pattern because it doesn't happen everywhere. Okay, questions about the idea? Let me put up a better picture to look at. So our definition of standing waves is it's a wave interference pattern that looks like a wave standing still, and it's called standing waves. So this is a time-lapse picture of a wave on a string. This is the kind of setup you're going to do in the lab. It's producing waves at one end, they're reflecting back from another end, and because this is time-lapse, this shows the position of the string at some different times. Just like my slinky moved through different times, so does that string. So let's get a little bit of lingo down, and let's see what we notice. First of all, let's define the equilibrium position. So when the string is still, before, say, you ever turn the frequency generator on, so when the string is perfectly still and not moving, this is the equilibrium position. So the equilibrium is there at the middle. That's the equilibrium. At some point in time, the wave is going to be up here at the maximum. I would draw in this picture, but there's no use because it won't come through the color. So at some point, it's on the top here, bottom here, and top here. So here's what it looks like at one extreme. So it might be up here. And then a half of a bit period later, or sometime later, that bit of string has moved down here, this one has moved up, and the whole pattern looks like this. So these bits of the string vibrate from here down to here, back and forth, up and down, and together it makes that standing wave pattern. Some features of this wave. We see that it has a well-defined wavelength, and one full wavelength is from here to here. So equilibrium crest, equilibrium trough, equilibrium. So this is a full wavelength. And standing waves will always have a well-defined wavelength. You can always hold a meter stick up to it and measure how long that wavelength is. We have places on the standing wave where it doesn't move at all. There's no motion. That's called a node. And if we were going to label those on a picture, we would just draw a dot and put an N next to it. So your nodes are the places on the standing wave where the string doesn't move at all, so it never ever moves. There are places on the string where it moves back and forth the most, so between here and here. Those are called the antinodes. The antinode is the opposite of a node. A node is no motion. The antinode is maximum motion. What else do we have? These waves always have a well-defined amplitude, so it does have a maximum height that you can measure. We can see that our nodes are separated by a half of a wavelength. So lambda over 2 between any two nodes. Antinodes are also separated by a half of a wavelength because they go crest to trough. And nodes and antinodes are separated by a quarter of a wavelength. Because it goes equilibrium to crest or equilibrium to trough. Okay, so I think, what else will we say here? Our nodes, where it never has any motion, at our nodes, we've always got perfect destructive interference. Okay, so always perfect destructive here. The antinodes, this is the place where we see kind of the maximum constructive. Okay, questions? Okay. A neat example of a standing wave, if you went through the review videos on simple harmonic motion on Bright Space, you would have seen this video. If you did high school physics, you've probably seen this video too. But let's have a look at this video, thinking about a standing wave.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge.
So right there is the standing wave.
Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
Okay, I actually think that's really sad. Like, I don't care much about the car, but it's sad that the dog didn't make it. So there was a lot of physics going on there. If you studied this in high school, or if you looked it up kind of maybe on an online source, the most common explanation for what happened is that the wind blew kind of puff, 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 and that made the bridge sway. That's not really what happened. The wind was blowing, certainly it was blowing, and he said in the video it was about a steady 35 miles per hour. So that was a steady wind. It wasn't pushing like you push a quid on a swing every so often. But the way that the wind was blowing hit the right frequency in the bridge, and it did cause some vibrations. It didn't cause it just to sway back and forth, but it caused one end to go down and one end to go up. That's called aerodynamic fluttering. Like, it's a really special form of a vibration that can happen. And because the wind was blowing at this frequency and it was humming across the bridge and it set this fluttering, it just made every subsequent vibration get a little bit bigger, just like the standing waves get bigger and bigger as you keep pumping it. Just like a kid on a swing will go higher and higher every time you push them at the right point. So then this brings in a whole bit about damping. When engineers build bridges now, you have to put damping into the structures because you don't ever want those resonances to get so big. You never want the fluttering to cause it to sway up and down by a lot. Who else cares about that sort of thing? People who build dance clubs. So people are dancing and you're rocking out to a really great song and everybody's jumping up and down at the right frequency. You don't want to hit the frequency of the dance floor. That's when dance floors collapse and people get hurt, right? So you build damping into all these structures. But now I've gotten away from this topic a little bit. That's kind of more about chapter 14. But anyway, it's really interesting stuff. Let's go back to the picture of the bridge. So at this point in time on the bridge, if we look at this picture and we think about what the slinky looked like, or that wave that I just had up on the picture, you see that one side is up, one side is down. And then a little bit of time later, this side goes down and this side goes up. There was actually a standing wave on the Tacoma Bridge, and that amplitude of oscillation just got bigger and bigger and bigger as time went on. Yeah, so that's kind of an application where that happened.
Is there a reason that the horizontal wave of the bridge and the vertical wave of the bridge didn't have any sort of adverse reaction on one another, like dampening wise?
It's really complicated, and that's sort of not something I would have studied. Like, I guess it all comes down to construction, right? Yeah, and the kind of supports on the bridge and all that stuff. Yeah, it's really complicated. Yeah. Yeah, something I would like to know more about for sure.
They do it with sound in some sort of types of sound engineering. They'll project the sound from a different angle to cancel out certain sounds in another area. So
Oh yeah, and that's something we're gonna talk about in class, sort of sound wave interference and where you get loud spots and quiet spots. Yeah, so that absolutely does happen in sound. And I would think that those are things thought about in modern bridge construction, right? You know, where the interference will be destructive to reduce that sort of amplification. Yeah. People going into engineering, you'll probably study at least a little bit about things like this, I would think. Okay, so just as a quick check before we move on, because you'll need to be able to do this sort of task as we go through our work. When we draw a standing wave, we always draw one extreme. So let's just get this one with the highlighter. So we draw one extreme first. Then we usually also indicate the equilibrium. The equilibrium is down through the middle. And then you also indicate the other extreme. So this is what pictures of standing waves will look like. Sometimes this other one will draw that with a dotted line, but you'll always see it like this. When you look at a picture of a standing wave like this, you should be able to figure out what the wavelength of the standing wave is from the given information. So have a look at this, and anybody want to toss out what they think the wavelength of this wave is?
One.
Okay, so very quick answer of 1 meter, agreement with 1 meter. Okay, there are different ways to get this answer. So one wavelength will go from a crest to a crest. That might be the easiest way to get it. So that's one complete wavelength. You see on the picture that that's 1 meter. You might do the whole thing. There's two wavelengths in 2 meters, so you could do it that way. You could go from an equilibrium back to an equilibrium, 0.25 to 1.25. That would be a meter. That's okay too. So you might go from here to here. So make sure you're okay with doing this sort of thing. That'll be something you'll need to do in the lab as well. So be able to look at the image of a standing wave and find the wavelength. So let's do a couple of examples. We have a standing wave on a 3 meter long string. It has a wavelength of 1.5 meters. Draw the wave on the string, show the nodes and the antinodes, and say where the nodes and the antinodes are. So this is going to get us comfortable with drawing these waves. So we know that the length of the string is 3 meters. L equals 3 meters. We know that one wavelength is 1.5 meters. And the first task we want to do is draw the wave on the string. If we look at these numbers, hopefully we recognize right off the bat that the length of the string is twice the wavelength. Okay, so wavelength is 1.5, length is 3 meters, the length is double the wavelength. That means there are 2 wavelengths on the full string. So if we want to draw it, we know we have to draw 2 wavelengths. So there's one wavelength. There's another wavelength. And then to finish drawing the standing wave, we'll typically draw like this. Artistically gifted, I am not. You don't have to be either. Just try and get the gist of it. Yep.
Do we have to start at a point of equilibrium?
Okay, so that's a good question. When we're talking about waves on strings, they will always have nodes at the end because the string is kind of floppy and we've got to pinch it at one end to keep it still. Yeah, good question. So nodes at ends. Indicate the nodes and the antinodes. So our nodes are the places with no motion. I'll color those in. So our nodes are here, 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 and here. The antinodes are the place with maximum motion. So here, 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 here. The antinodes are exactly in between any two nodes. To find the locations of those, we'll have to put a coordinate system on our problem and an origin. So I'm going to call this point right here at the left end of the string, I'm going to call that x equals 0. So my nodes are located every half wavelength apart. So my nodes are at 0, lambda over 2, lambda, 3 lambda over 2, and 2 lambda. So those are the positions of my nodes, here, 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 and here. So kind of every bump is a half of a wavelength. If I put in my lambda as 1.5 meters, I get 0.075, 0.75 meters. Zero, 0.75 meters, there we go. 1.5 meters, 2.25 meters, and 3 meters. So those are the positions of the nodes. For the antinodes, so our antinode goes from an equilibrium to a crest. That's a quarter of a wavelength. So the first one is a quarter of a wavelength down the line, lambda over 4. And then antinodes are separated by a half a wavelength. So this one is going to be located at a half of a wavelength plus a quarter, so 3/4 of a wavelength. And then the next one is 5 lambda over 4. And the next one is 7 lambda over 4. If we put in lambda, we get 0.375 meters, 1.125 meters, 1.875 meters, and 2.625 meters. So those are the positions of the antinodes. Okay. Questions about that? Yeah.
When you draw the antinodes, does the dots need to be on the main wave or the reflection, or does it not matter?
Yeah, so if I was going to put dots for the antinodes, I would probably put the dots at the both extremes. If you only put them on one side, like if you drew them all down here, that would be okay too. I would probably put it on both. Yeah. Okay, questions? All right, we're going to talk kind of a little bit about getting the parameters on the correct lengths and frequencies. And then we're going to do more examples about this stuff. We'll start putting it all together. And we'll bring in part of V equals tension over mu as well. So we'll start bringing the problems up a couple of notches. So this is going to be a nicer look of what I tried to do with the real Slinky. And let's just have a look at those standing waves on the Slinky. This is from a simulation at St. Mary's University. They've got a pile of nice simulations if you want to check it out. So here's the first standing wave, happens at a certain frequency when you shake it up and down. Notice you got the nodes at the two ends, the antinode in the middle. We change the frequency, we get a new standing wave. This time it's a full wavelength, nodes at either end, one node in the middle, and antinodes between those. Okay, now we've got another node squeezed in there. There's one here and one here. So as we change the frequency, we keep adding another half of a wavelength. So that's how you make more and more standing wave patterns. So you get more waves in there. And then you can keep doing that all day. Keep changing the frequency, keep getting more of a wave in there. So what we're going to do is we're going to write down what happens at the ends. We're going to draw the waves, and we're going to get expressions for the wavelengths and the frequencies.
How does transferring the energy from simple harmonic motion to something that has like a more rigid body that wouldn't experience the same sort of frequency, how does that energy interaction work?
So like if we were transferring a wave along like a rod or a desk or something like that?
The easiest example I can think of is like engine mounts.
Yeah.
Before they had dampening because if you put too much power into the engine, it could affect the way the car moved because it was
Yeah.
transferring the energy or the frequency of the engine vibrating into the body of the vehicle. How does that energy interaction work? Is it a destructive because it's passing into something that has greater rigidity in the structure of its movement, so it can't vibrate at the same frequency, or?
So energy certainly travels along solids. You have to analyze it in a different way. You essentially take, a string has a linear mass density. A solid would have either Young's modulus for a solid. That would describe the solid and how waves transfer through a solid. So you would do an analysis thinking about it that way. It's in your book if you want to read through it. Yeah, it's interesting stuff. Okay, so to make a standing wave, we're going to start with the idea that we have to hold the string at both ends. That sort of makes sense because if I tried to make a standing wave on a slinky and we didn't have somebody holding the other end, it would just fall down. Okay, so we've got to hold both ends. It needs to be fixed at both ends. When we say it's fixed at both ends, we're talking about what happens at the ends. That's called a boundary condition. So the word boundary condition talks about what's happening at the ends of the string. So the boundary condition is that the ends have to be fixed. That means at the ends we have nodes. Okay, so that's our boundary condition. That's pretty important. If we're looking at waves on a string, we're going to say that the string has a length L. And when we make our different waves, each one is going to look a little different because we change the frequency and we get another bit of the wave in there. Our first wave will go from a node to a node, and it looks like this. This is the first wave we get. This is the simplest wave. This one is called the fundamental. As we change the frequency, we still have to have two nodes at either ends. To get more of a wave in there, what happens is that we add an additional node. That node is going to go in the middle, and our new wave looks like this. Okay, so we've added another half of a wavelength. To get to our next wave, we add another node or another half of a wavelength. And then I'll only do one more, so node, node, and node. So you can keep drawing this pattern all day. This is how it changes from mode to mode. These are the waves we saw in that animation from St. Mary's. These sets of waves, they have a bunch of different names that you'll hear in different books from different people. Sometimes they're called the modes or the harmonics or resonances. And then sometimes those words might go together, like harmonic modes or harmonic resonances, so you might hear those different things. Musical people might throw in the words overtones, so those could happen as well. Different books use different things. We're going to develop the theory of waves by looking at and describing each one of these single waves. But in reality, if you're playing guitar or something, you don't ever just have one wave on the string at a time. You have a whole bunch of these waves at the same time, and they all interfere, they all come together. When we spend a little bit of time talking about music, we'll see that. So our approach, and we're going to start this on Monday, is we're going to look at the wavelength in relation to the length, and then we're going to tie the frequency to the wavelength, and we're going to get our patterns there. Okay, so we'll quit there for today, and we'll be back on Monday.